In this video, we're going to look at some of the properties of the period 3 oxides. So I want you to take a minute, go back to what we did on the first video where we looked at the structure and bonding. So just have a flick back and remind ourselves of that flow chart. So take 2 minutes, just think about all the different types of bonding. Now remember, we're going to be looking at the period 3 oxides, and in the last video when we formed those period 3 oxides, we looked and we thought we were making some from metals and some from non-metals, and therefore we are going to have compounds that contain metals and non-metals and are ionic, but some that contain non-metals only because they're made from a non-metal with oxygen, which is also a non-metal, and so we're going to have some that are covalent. So if we go back to our page here, and we're looking at them, we've got sodium oxide, magnesium oxide, and aluminium oxide. They would be metal oxides, so that would be metal and oxide non-metal. And so we would be looking there at our ionic structures. So here we've got ionic or electrostatic force of attraction between oppositely charged ions. So strong forces between those oppositely charged ions. Squeeze that in there. And we call that structure, when we're asked for the structure, don't just write the bonding, we call that structure giant, which is why it's strong ionic lattice. And then on the other side, we've got our silicon oxide, phosphorus oxide, and sulfur oxides. So they're all non-metal with non-metal. Now you can see there's a little bit of a division here, there's a line, and that's because silicon oxide, so silicon 4 oxide or silicon dioxide, is macromolecular. So don't forget carbon, diamond, silicon, silicon dioxide, macromolecular. Oops, that should have gone in the bottom bit, shouldn't it? Not there. So let's just get rid of that and put that into the right section, the structure at the bottom, macromolecular. And the bonding then is many strong. So covalent is the bonding bonds. And they're between the atoms of silicon and oxygen, so between the atoms. And because it's a large giant lattice, it's a strong thing. And then we've got our phosphorus oxide. So this is called phosphorus 5 oxide and sulfur 6 oxide or sulfur trioxide. These are all simple molecular. And so their intermolecular forces would be weak, but they have covalent bonding, but they have weak intermolecular forces. So let's have a look. We've got the metal oxides. So remembering our metal oxides are ionic, and so they're going to have high melting points. This is because the strong electrostatic force of attraction between oppositely charged ions require a lot of energy to break. SiO2 has a higher melting point than P4O10 because it's macromolecular, whereas P4O10 is only simple molecular. And that doesn't mean that there's more bonds to break. We're not breaking the bonds in the P4O10, we're breaking intermolecular forces, where in SiO2 we are going to break bonds. So we've got our full stop there. I could have written simple molecular over 2 lines. So we've got the many strong covalent bonds in SiO2, that's between the silicon oxygen atoms, require more energy to break than the weak. And P4O10 is symmetrical, so van der Waals forces between P4O10 molecules. So we've got one P4O10, so you can imagine it like this little blob, and then we've got another P4O10, and all we're doing is overcoming a weak force between the two. Whereas in SiO2 we've got Si, and then it's sort of in a tetrahedral lattice. There's oxygens all around, joined to more silicons, and then And then, you know, there's like all this interconnection, and we've got to break all of this up in order to break up the macromolecular structure. When we compare P4O10 and SO3, we find that P4O10 has a higher melting point than SO3. And even though they're both simple molecular and both SO3 also symmetrical, SO2 not symmetrical, but SO3 symmetrical, because SO3 is trigonal planar like this. Yeah. P4O10 has a bigger molecule than SO3, and therefore it has more electrons than SO2 or SO3. There's a typo there, but it doesn't matter. If it was SO2, you could do the same argument. Therefore, P4O10 will have stronger van der Waals forces. Between the molecules. So make sure that your structure and bonding is really strong. For this topic, you're going to get a lot of overlap with structure and bonding questions. You're going to be asked to compare structure and bonding between either the elements or the oxides, to discuss them and to explain their boiling points and their properties as a result of that.